Okay, this is another way to parameterization. It's a graphing parameterization. Look, suppose we have a function c is equal f and x comma y, and we are doing the parameterization. We call x equal u, y equal b, and c is equal f and u comma b. Okay. When you are doing the parameterization in this way, the domain of this, look, the domain of this is the shadow of S. The S is surface of the XY plane. In this case, actually, this is X and this is Y. The domain is this. Domain for this parameterization is this region, because you suppose que is X and Y the parameter, right? Therefore, the domain is the shadow of S on the XY plane. Okay, this is example 1. Suppose I am doing the parameterization using graphing parameterization of this. It's obvious that this is the paraboloid, and this paraboloid open down, 1, 2, 3, 4, open down like that. Okay, paraboloid, open down. I call, for example, I call x is u, y is b, c is equal 4 minus u squared minus d squared. What about domain? Domain is the shadow here, the shadow onto the xy axis is the circle. In the center is in the origin, and the radius is 2, because when the c is 0, 4 minus u squared minus b squared, u squared plus b squared equal positive 4 is a circle where the radius is 2. Okay, this is the domain. Radius 2 minus 2. This is the domain D of this parameterization. So this is a parameterization, and its domain is this figure. Okay. Okay, now our goal is to determine the formula for the surface area. Okay, we have here a surface expressed like a vector value function using two parameters, u and v. This is the parameterization domain. Now, if you want to find the surface area, here you take here one elementary area, infinitesimal area. This is this rectangular. This dimension is du, and this dimension is dv. When you are doing the parameterization is like a chain verb. You change ub to xyz verb. Suppose that this rectangle have an image of this. Okay. Now, in order to find this, we plug it in here in the vector value function, no? But this is differential, so you need to differentiate this. If you differentiate, for example, the vector value function r, differentiate in u, and multiply by du. And for example, this is this segment. RU DU, and this is similar, is RB dB. Is this second. In order to find the area here, we apply a cross product. Okay, DS, let me call it here DS. Don't confuse it with the little x, the R-link. Now this is capital S with the two dots here that represent the surface area elementary. This is the area for this elementary. It's a cross product of RU cross product RB multiplication by DU dV. If you want to find the total surface area, is S is the double integral and the domain D of the function that now is RU cross RB du dv. Okay, and this is the formula that we are using to compute the surface area in general, using no graphic parameterization, using general parameterization, using U and V. Okay, suppose now the case in which you have graphing parameterization, and this is the vector value function that represents the surface. You differentiate with respect to x, differentiate with respect to x is 1, this is 0, and this is the partial derivative with respect to x, like something like that. And likewise, you differentiate with respect to y, is 0, f1, and this is fy. And now you perform the cross product. One 0 fx 0 1 fy. And when you perform the cross product, this is I. This and this 0 is fx minus let me see, 0 fx minus j, this is fy plus k this is just 1. So the vector is the vector minus fx, comma, minus fy, comma 1. And the magnitude of this vector, is square root this component square plus this component square plus 1. And the formula to compute the surface area is then, look, surface area is equal the double integral in the domain D, and remember the domain D is the shadow on the xy axis of this graphic of the square root 1 plus fx squared plus fy squared dA is dx dy. Wow, this is the formula to find the surface area of this any surface. Okay, in this elemental example, you need to find this area, surface area of this triangle. Okay, we're using the formula. The formula contains f of x, f of y. Who is f? You solve for c. C is equal 1 minus x minus y. This is f. This is f, and x comma y is c, and f of x is the derivative is with respect to x is -1, and with respect to y is exactly the same, -1. And when you go with the square root, f of x squared plus f of y squared plus 1 give me square root 1 squared plus 1 squared plus 1 squared, que is radical 2. So the formula for the surface area is, this is S, is the double integral of this expression, the radical 3 dx dy. And the region is obvious que is this region. And you cannot integrate. This is okay. This is the constant surface area outside the radical 3 double integral d dx dy. And this is the area for this triangle. And the area for this triangle is 1/2, no? Because area is equal 1/2. Multiplication height and base is 1/2. So what is the surface area? The surface area is radical 3 over 2. Okay, let's do the verification of this answer using geometry. This is the triangle, equilateral triangle. This is 60 degrees. 60 degrees, 60 degrees. See, this distance is 1, this distance is radical 2. Radical 2, radical 2, and radical 2. Well, actually it's radical 2 over 2, and radical 2 over 2, and total is radical 2. To find this distance, I want to call x. You apply trigonometric tangent, 60 degrees, I know is radical 3. By definition is x divided by radical 2 over 2. Therefore, x is equal multiplication this and this. Radical 2, radical 3 over 2, or radical 6, whatever you want. Now the area is equal 1/2 the base times the height. 1/2. The base is this base, radical 2. And the height is radical 2, radical 3 over 2. Radical 2 times radical 2 is 2. And this 2 is cancelled and stay radical 3 over 2. Exactly like that.